All right, folks, continuing on here, we're going to now look at section 12.2, polar coordinates. So this section is focusing exclusively on something that you learned in trigonometry, and that would be polar coordinates. As a result, this section is calculus free. However, everything I'm going to review in this section is vital for understanding the next section. In the next section, we start to look at the calculus of polar coordinates. So let's get started. Polar coordinates, remember, they're of the form r theta, where r is a directed distance and theta is a directed angle. Polar coordinates are predicated on the polar coordinate system, and the polar coordinate system has a polar axis and then something called the pole. So what I'm going to do now is I'm going to make a quick trip to the chalkboard before continuing. All right, folks, hey, remember polar coordinates have the form r theta. R is a directed distance. Theta is a directed angle. So everything in the polar coordinate system is predicated off of this structure here. This is called the polar axis, and that is the pole. So here's what the deal is. You can take your polar axis and you can give it a rotation. So I'll use this to represent the polar axis. If you take it and you rotate it in this direction, well, remember, theta would be positive. If you take the polar axis and you rotate it in this direction, theta would be negative. That's a directed angle. So let's say I kind of take my polar axis and I give it a rotation to right there. So I have it stop here. There's theta. So theta is positive. It's a directed angle. And let me find a point now. Let me just find some arbitrary point. I'll plot it right here. So that's some arbitrary point, r theta. We see theta is positive. It's positive rotation. And then right here, that's our directed distance, r. R would have a positive value. It's a directed distance. If I plotted the point, you know what, let me do a little erasing here. If I plotted the point, so this is where my polar axis stops. If I kind of extend down in this direction, and I plot a point right here, P, it still has the same directed angle, theta, but then this distance here that's r, but in this situation, r would have a negative value. So here's what I'm getting at, and I'll stress this when we start to plot some polar points. Do the rotation of the polar axis first. So do theta first. See where the polar axis comes to stop. If r is positive, then you will go along the final resting place of the polar axis. That's if r is positive. If r is negative, you come in the opposite direction of where the polar axes stop. So that's what we mean by a directed distance. But let's head back to the slides now and see what's next. All right, that was a quick review of our polar coordinate system, the polar axis and the pole. Keep in mind what I said about the directed distance and the directed angle. Now, it's a convention to superimpose the polar coordinate system over our familiar XY coordinate system. Remember, there are many different names for the XY coordinate system. It can be called the XY coordinate system, the XY plane, the Cartesian coordinate system. But in any event, we're going to superimpose the polar coordinate system over top of the Cartesian coordinate system. And this is done by placing the pole at the origin, and the polar axis would then start off lying on top of the positive x-axis. So it looks something like this. So that's what it looks like when we go to superimpose the polar coordinate system on top of the Cartesian coordinate system. A little bit more. Now, the polar coordinate system uses radial lines coming from the pole, and these radial lines represent the familiar angles that we know from the unit circle. Remember those familiar angles from the unit circle? Pi over 6, pi over 4, pi over 3, 2 pi over 3, etc. One more thing the polar coordinate system will use, and it's concentric circles to represent distances from the pole. So like a scaling, if you will. So here's what the complete polar coordinate system looks like when it is superimposed on top of our familiar Cartesian coordinate system. So you see the radial lines. So that in quadrant 1, the first radial line, that would match up with a theta value of pi over 6. The second radial line matches up with a theta value of pi over 4. The next one matches up with a theta value of pi over 3, etc. And without any scaling being here on the concentric circles, let's say the innermost circle would be a radius of 1. The second one would be a radius of 2. The third one, a radius of 3. So let's do a quick example of just simply plotting polar points. And in this example, I'm going to stress exactly how to plot them, what you should be thinking, because how you plot them and what you should be thinking, it's going to set up our eventual graphing of polar equations, which in turn is going to set up what happens in the next section. So this example, we're going to plot 4 polar points. Polar point 2 pi over 4, the polar point 2 3 pi over 4, the polar point 2 5 pi over 4, and the polar point negative 2 pi over 4. So let's head off to the chalkboard to plot these polar points. Okay, in this example, it's just to basically plot 4 polar points. I'm going to try to color code these. So part A, I'm using blue chalk to plot the point 2 pi over 4. In B, I'm using yellow chalk to plot the point 2 3 pi over 4. C, I'm using this reddish colored chalk to plot the point 2 5 pi over 4. And then in D, I'm going to use this greenish colored chalk to plot the point negative 2 pi over 4. So I did my best to draw a polar coordinate system. And remember, we superimpose it on top of the familiar XY plane. So the polar axis, we put the pole at the origin, and the polar axis starts off on the positive x-axis. And then, I've just labeled those familiar angles in quadrant 1. So these are the radial lines that I was talking about. So if my polar axis rotates up to here, that's pi over 6. To here, it's pi over 4. Here, it's pi over 3. We know here would be pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, etc. And then the concentric circles. I'm going to say that every point on this circle is 1 unit away from the pole, so r is 1. This would have an r value of 2, and that would have an r value of 3. So, part A, plot the point 2 pi over 4. So I really want to stress how I want you to start to think of this. Do the directed angle, do that first. So your polar axis See, it gets rotated to pi over 4. So this is its stopping point. R is positive. Since R is positive, I move 2 units away from the pole along the polar axis. And that would give me, that is the point 2 pi over 4. For B, to plot the point 2, 3 pi over 4. So I take my polar axis and I rotate it to 3 pi over 4, which is right here. Now let's see, R is a positive 2, so I move 2 units along the polar axis. And it gives me, that's the point 2 pi over 4. Plot the point 2, 5 pi over 4. So I take my polar axis and I rotate it to 5 pi over 4, which brings me to right here. R is a positive 2, so I move 2 units along the polar axis, and it gives me that point right there. So in D, plot negative 2 pi over 4. Do the rotation of the polar axis first. So the polar axis rotates to here. But now R is a negative 2. So negative 2 means I go in the opposite direction of the stopping point of the polar axis. So I come 2 units in the opposite direction, and it gives me that point. So this point had polar coordinates 2, 5 pi over 4, and this point had polar coordinates of negative 2 pi over 4. It's the same point. The same point is represented in 2 different polar coordinate representations. In fact, this one polar point, or any polar point, there are an infinite number of ways to represent it, which means polar coordinates are not unique. So let's head back to the slides, and I bet that's the first thing I mention when we get back to the slides. All right, hopefully we saw in that last example, what I was really stressing is you do the theta first, then you do the r. It's really, I want you to start thinking that r value, the directed distance, it's going to be considered a function of theta, whatever theta is. So one more thing from the last example. The last example illustrated a basic fact about polar coordinates. That is, polar coordinates are not unique. Rectangular coordinates, or if you prefer, call them Cartesian coordinates, they are unique. Now, since we do superimpose the polar coordinate system on the familiar xy plane, we should be able to establish relationships between polar coordinates and rectangular coordinates. And if we can establish a relationship between polar coordinates and rectangular coordinates, then by extension we'll be able to establish a relationship between polar equations and rectangular equations. So let's head to the chalkboard to look at how polar coordinates and rectangular coordinates can be related. All right, folks, because we take our polar coordinate system and we superimpose it on top of the xy coordinate system, the Cartesian coordinate system, we should be able to get a relationship between polar coordinates and rectangular coordinates. So here's my rectangular coordinate system, and I went ahead and gave my polar axis a rotation, and I've plotted a polar point, r theta. So that means from here to here is the directed distance r. Notice in rectangular coordinates, or Cartesian coordinates, this same point would be represented as xy. So here's what that means. it means this distance is y, and this distance here is x. So to come up with the relationship between polar and rectangular, excuse me, it looks like, well, some right triangle trig. We know by looking at that right triangle, we know cosine theta is adjacent over hypotenuse. We know sine theta is opposite over hypotenuse. We also know tangent theta is opposite over adjacent. Heck, we even know x, y, and r are related to each other via the Pythagorean theorem. X squared plus y squared equals r squared. So if you look at this and you multiply both sides of this equation by r, you get x equals r cosine theta. If you look at this equation and multiply both sides by r, you get y equals r sine theta. Folks, this is exactly how you convert from polar coordinates to rectangular coordinates. So this is how you convert from polar to rectangular. What do these two equations do for us? Well, what they do is they tell us how to convert from Cartesian to polar. So it's going to be very, very straightforward and fairly easy to take polar coordinates and convert them to Cartesian. It's not so bad to take Cartesian and convert them to polar. We just have to be a little careful. So let's head back to the slides and see what examples we have. All right, you probably remember those conversion factors on how to convert from polar coordinates to rectangular coordinates and vice versa. You probably remember that from trigonometry. But let's do an example here. Let's convert the polar point 4 pi over 6. Let's convert that to rectangular coordinates. So here I go, heading off to the chalkboard to do this one. All right, folks, in this example, we were asked to convert the polar point 4 pi over 6 to rectangular coordinates. It's a pretty straightforward process. In fact, let me just kind of foreshadow the next section when we do the calculus of polar coordinates. These conversions, knowing these conversions is going to be very, very important. It's going to make your life a lot easier in doing the calculus of polar coordinates if you know these conversions. Continuing though for this one, r is 4, theta is pi over 6, so just toss that in here. r is 4, theta is pi over 6. You know cosine of pi over 6 is square root 3 over 2. And you know the sine of pi over 6 is 1/2. So you get x is 2 square root 3. Y is 2. So the rectangular coordinates for that point would be 2 square root 3, 2. Told you it would be very straightforward, very friendly. So what I'd like you to do now is pause the video and in section 12.2 exercises, go give number 26 a try. After you do it, restart the video and I'll be here cranking through it. Alright folks, in number 26 you were asked to convert the polar point 1 2 pi over 3 to Cartesian coordinates, or rectangular coordinates. So again, x equals r cosine theta. Y equals r sine theta. R is 1. Theta is 2 pi over 3. So you know the cosine of 2 pi over 3, you know that is negative 1/2. You know the sine of 2 pi over 3 is square root 3 over 2. So the Cartesian coordinates, or rectangular coordinates, is simply that. Not really a surprise, because if you kind of thought ahead a little bit, this point is a point that's on the unit circle. But we got some practice using really important things to know. So let's head back to the slides and let's see what's next. All right, after doing this example, converting 4 pi over 6 to rectangular coordinates and doing number 26, hopefully you're seeing or you're remembering to convert from polar to rectangular. You know, it's pretty friendly. It's a piece of cake. The next example, let's convert the rectangular point 3, -1. Those are rectangular coordinates. Let's convert those to polar coordinates. We have to take care in doing this. So I'm going to head off to the chalkboard to crank through this one. And, let's see what we come up with. All right, folks. And well, this wasn't an example. Oh, yes, this was an example. Convert the rectangular point 3, -1. Convert that to polar coordinates. This is just a little more. It's not as easy as the other conversions. So here's what I always do first. When I'm taking a rectangular point and I'm converting it to polar, the first thing I do is just quickly plot the point. So it's roughly right there. And the reason why I do that is because I know theta is a directed angle. I know r is a directed distance. So with that said, this is what we use to convert from rectangular to polar. So let's see, x squared, so we'd have a 3 squared plus a -1 squared equals r squared. So 10 is r squared plus or minus square root 10 is equal to r. I don't know which to use until I get my directed angle theta. So tangent theta, well, that's a -1/3, so I know theta is the inverse tangent of -1/3. Make sure your calculator's in radian mode. And I get theta is approximately -0.322. All right, so now I can come up with polar coordinate. I can come up with polar coordinates for this point. If I use that negative value of theta, remember, negative value, my polar axis would rotate in this direction. My polar axis would be stopped at this point. So I'd use the positive r to come along the polar axis. But if you were told theta has to be positive, so theta has to be between, say, 0 and 2 pi, well, you would have to take your polar axis. I mean, you can't rotate it this way. That's a negative measure. So you'd have to take your polar axis and you'd have to rotate it to about right here. And if that's where the polar axis stops, to get to this point, you would be using a negative r. So that would be negative square root 10. how am I going to get that angle measure? How am I going to get the rotation for my polar axes? That's right, you just simply add pi to that. And if you add pi to that, you get something close to a 2.82. Remember, polar coordinates are not unique. There are many ways to represent that point in polar coordinates. So here's what I want you to do now. I want you to do number 36 here in section 12.2. And I believe in the directions to number 36, the directions say something about represent the polar point in maybe two ways. So come up with two polar coordinates for it. After you do number 36, restart the video. I'll be here at the board. I'll end up showing three different polar representations for the point given in 36. Pause the video, do 36. After you've done it, restart the video. I'll be here at the board working through it. All right, folks, on number 36, you were given the point -8, square root 3, -8. The first thing I would do is quickly plot the point so I can just see where the point is living. It's going to be kind of important for when I come up with the polar coordinates, so I might as well plot the point so I can see where it is living. So, we know we're going to use x squared plus y squared equals r squared. That'll give me my r. And tangent theta is y over x. Hopefully that can give me my theta. So, -8 square root 3 squared plus -8 squared is r squared. I think -8 square root 3 squared, 64 times 3, that's 192. -8 squared is 64. So this is 256 is equal to r squared. Yeah, it's kind of friendly. Plus or minus 16 is equal to r. Well, that's not too bad. Over here, tangent theta is -8 over -8 square root 3. So tangent theta is 1 over square root 3. That's something I think I could figure out from the unit circle. It's pi over 6. I'm also going to list 7 pi over 6. Because I know this tangent of 7 pi over 6 is also 1 over square root 3. So the book said in the directions come up with two different ways, and I said I would end up doing 3 ways. So let's look at using a theta of pi over 6. So my polar axis gets rotated to pi over 6. What would r have to be to get me down here? That's right. It would have to be a negative to get me to that point. So we have -16 pi over 6 as one representation. Well, what if I wanted to use a positive 16? Well, that would be my polar axis getting rotated to 7 pi over 6. Then I would use a positive r to come along the polar axis to get me to that point. So that's 7 pi over 6. Or, yeah, I'll put an or in here. And then let me put an or here. What if I gave my polar axis this kind of a rotation? I would be using a positive r. So what is this rotation? That's right, it's -5 pi over 6. And so I know your book said come up with 2 of them. I bet your book has 2 of those 3. Remember, there are an infinite number of ways to represent polar points. So let's head on back to the slides and let's see what's next. All right, so we've done our conversions. Keep in mind we can convert equations. We can convert equations now, rectangular equations to polar equations and vice versa. So, I don't have this example written down, in a slide here, but I'm going to head off to the chalkboard right now to do a couple of your homework problems on going from a rectangular equation to a polar equation, or from a polar equation to a rectangular equation. So I'm going to head off to the chalkboard and do a few of your homework problems. Hi folks, sorry I didn't have these actually written down on a slide, and I told you that we were going to do 41 and 51. Because now that we know how to convert points, rectangular coordinates to polar coordinates, or polar coordinates to rectangular coordinates, we can do the same thing with equations. So number 41, you were given this polar equation and you were asked, hey, convert this to a rectangular equation, or an equation with Cartesian coordinates. So when I look at this, the first thing that pops into my head, I wish I saw an R here, and I wish I saw an R there. Because if I saw an R right here, if I had 2r sine theta, I know r sine theta is y. And if I had an r here, and it said 2r cosine theta, I know r cosine theta is x. I don't see an r there, but I want to see an r there. And the best way, the legal way, to get an r there is just multiply both sides of the equation by r. That would give you an r squared is 2r sine theta plus 2r cosine theta. Folks, you know r squared is x squared plus y squared. That's a y. That's an x. So there's a rectangular equation. There's nothing wrong with that, but I'm going to go just a little bit further. I'm going to subtract 2y, and I'm going to subtract 2x from both sides of the equation to get an x squared minus 2x plus a y squared minus 2y equals 0. And then I am going to say, why don't we complete the square here, and why don't we complete the square there? So the process of completing the square, I would have an x squared minus 2x. So remember, I would take half of this, so half of that is negative 1. Square it, negative 1 squared is 1. So I'd have to add a 1 in here. Likewise, when I complete the square here, I'm going to end up with a plus 1. So if I add 1 and add 1, I'm really adding 2 to the left side of the equation, so I better add 2 to the right side of the equation. 0 plus 2 is just 2. So now I have a perfect square here. X minus 1 quantity squared. This is a y minus 1 quantity squared equals 2. And I remember from college algebra, this equation represents the equation of a circle. It has a center at 1, 1. And it has a radius of square root 2. Alright, that was kind of fun. In 51, you were asked to take the equation that was given to you in Cartesian coordinates, or rectangular coordinates, and to convert that to polar coordinate equation, so a polar equation. Well, just straight away, you know what y is. Y is r sine theta. You know what x is. X is r cosine theta. I don't like the looks of that at all. That equation doesn't look friendly. I'm going to multiply both sides of that equation by r cosine theta to get r squared sine theta cosine theta equals 1. And because I know what's coming up, I'm going to divide both sides of this equation by sine theta cosine theta. I kind of like to get my r by itself on one side of the equation. Now granted, that's an r squared, but at least I have the r over on the left side. And then I'd go one more step just because it's fun. 1 over sine, that's cosecant. 1 over cosine is secant. And I'm going to stop there. I'm not going to go any further. That looks like it's a good representation. So there were a couple of your homework problems, converting equations. So now let's head back to the slides and see what we're going to do next. All right, continuing on, now we're going to start talking about polar graphs. So I'm going to have a lot of words on this slide, so bear with me. Folks, when we graph polar equations, and for future work as well, and when I say future work, I'm talking about not only the next section, the calculus of polar coordinates, but it's also laying the foundation for what you're going to see in Calc 3 when you start to take things into space. So we start to have a third component, a third coordinate, 3 dimensions, in other words. It's going to be important to think of the equation as being in the form r equals f of theta. I've already mentioned this once. And here's the process that I really would like you to think about. When graphing, when doing polar graphs, imagine a radius swinging around the origin in a counterclockwise direction. The polar graph, the curve, is being traced out by a point that is attached to this turning radius. And this point is free to move toward the pole, or origin, or away from the pole. Its movement is dependent on the behavior of the function f of theta. All right, now in what you've dealt with so far up to this point in time have been rectangular coordinates, and y is a function of x. Y is a function of x. You know, we're used to the idea of technically of a point x moving along the horizontal axis. So you think you're moving from left to right, and y is the directed distance measured up or down, dependent on the behavior of the function f of x. So the distance, that y value, whether you're above the x-axis or below the x-axis, was dependent on f of x. So really, I like to say at this point in time that when you've been graphing functions, y equals f of x, you've been thinking and you really have been living in the terms of a quote left to right world. So you're moving from left to right, and then the graph is either moving up or down. So it's a left-right world, up and down. With polar coordinates and r equals f of theta, remember, r is directed distance, theta is a directed angle. You can think of an angle theta swinging around counterclockwise, and for each theta, we measure out the directed distance, f of theta. R is f of theta. R is the directed distance. So we can think in terms, this is for polar graphs, of the polar axis moving around and around, and then the polar graph being traced out by either moving, as the polar axis is moving around and around, in towards the pole or out away from the pole. And then I say in many cases, f of theta, we're going to deal with an expression involving sine or cosine, sine theta or cosine theta. Because of that, it is very useful for you to have a good grasp of sine theta and cosine theta as theta increases from 0 to 2 pi in increments of pi over 2. So what I'm going to do right now, I'm going to take a little break, and I'm going to head off to the chalkboard to kind of give a demonstration of what this slide is saying. So let's head off to the chalkboard and see what we can come up with. All right, folks, there were a lot of words on that slide, and I wanted to take a little bit more time to go through this. This is really, really kind of important. In the rectangular world, y is a function of x. Y is either it's the distance above the x-axis or below the x-axis. So here's what really has been happening when you've been graphing functions of x. You are moving from left to right, and as you move from left to right, you are tracing a graph that is either above the x-axis or below the x-axis. So you can kind of think, if you just look at a real friendly example, f of x equals x squared. You can kind of think that there's something attached to this vertical line that as you move from left to right, this function, well, the y value is dependent on what x is. The height above or below the x-axis, it is dependent on x. It's a function of x. So as you move along here, this is tracing out, and I'm kind of losing it there. It's tracing out the curve in that fashion. The polar world requires you to think completely differently. The polar world is not a left-right world at all. It's not an up-down world at all. The polar world is predicated on the polar axis going around and around. Your polar axis goes around and around. That is not left-right. It's around and around. And as the polar axis goes around and around, imagine that the curve that's being traced by the polar equation as you're going around and around, that curve is free to move, away from the pole or towards the pole. So as it goes around and around, it's tracing out, going away from the pole and then back towards the pole. And it continues to go around and around. Really, really important. Rectangular, left, right. And you're moving up or down. Polar, around and around, away from the pole or in towards the pole. It's really kind of important. Let me just kind of foreshadow something real quick. In the rectangular world, you found these things called a relative max or a relative min. Relative max was the high point, relative min was the low point. So like right here. That was a relative min. That's the rectangular world. In the polar world, a relative max is not a high point, because in the polar world, it's around and around, away from the pole or in towards the pole. So in the polar world, a relative max would be a point that is farthest away from the pole. And a relative min would be the point that is closest to the pole. And if you hit the pole, I mean, man, you can't get any closer to the pole than hitting the pole. So please think of it this way. Let's head back to the slides and see what's next. All right, let's check out this example. Graphing r equals 4 cosine theta. And it says also convert to a rectangular equation. So we're just going to practice that as well. So you know what? Back when I learned this stuff, I had to have memorized polar graphs and what the polar graphs produce. So I had to have memorized, did it produce a rose curve, a cardioid, a lemashone, a dimpled lemashone, and lemashone with an inner loop, a lemniscate, a circle. Thankfully, we have graphing calculators now. While it'd be nice if you knew that stuff, I'm going to rely on a graphing calculator to give me the graph of my polar equations. So let me call up my graphing calculator here. And all right, so first thing, I need to put my calculator into polar mode. So let me come down, and over there's polar. All right, so now when I hit my y equals button, notice it's an r equals, and I wanted to graph 4 cosine theta. Now my variable button is now a theta button. See, theta. Let's go check out the window. Okay, just like, remember in parametrics, we had a T-min, a T-max, and a T-step. Well, we have the same thing in polars, except it's a theta-min, theta-max, theta-step. So by default, the first time I look at a graph of a polar equation, I always look at it on the interval of theta-min, 0, theta-max, 2 pi, and then I increment my thetas by pi over 32. Let's see, x-min, I have x-min -4, x-max 4. You know what, I'm just going to give it a first look with the x-min, x-max, y-min, y-max. So here comes the graph. All right, that was graphed pretty quickly. It kind of looks like an ellipse, but you know what? I'm gonna do one of these things now. I'm gonna look at it in a square viewing window. So let me do 5. It's really a circle. It is really a circle. So my first viewing window, it looked like an ellipse, but when I made a square viewing window, I can see it's a circle. A square viewing window will give a true representation. So you know what I'm going to do right now is I'm going to head off to the chalkboard, and I am going to I'm going to finish this example, which is to convert this to a rectangular equation. Okay, this example, we were given the polar equation r equals 4 cosine theta. We graphed it. We saw what the graph looked like. It looks something like this. I'm so happy we have graphing calculators nowadays to do polar graphs. And I said it kind of looks like a circle. The second part of the example was to take this and convert it to a rectangular equation. Well, just like the one we looked at earlier, I would love to see an r here. So I multiply both sides by r. I get an x squared plus y squared equals 4x. And if I subtract the 4x on over, and you know what I'm going to do? I'm going to complete the square here. So that's an x squared minus 4x. See, half of that is -2. -2 squared is 4. So I need to add 4. Then that is an x minus 2 quantity squared. Y squared equals 4. I know this rectangular equation tells me we have a circle centered at the point 2, 0 with a radius of 2, which is exactly what the graph looked like. It looked like a circle centered at 2, 0 with a radius of 2. Okay, so now, just to practice doing some graphs of polar equations, why don't you give number 58 a try and see what you come up with. All right, folks, before we go any further, let's look at number 58 to get the graph of number 58. So let's look at the graph of number 58 here real quick. So number 58, see the polar equation was r equals 2 minus 2 sine theta. And let's see, my window, that's 0 to 2 pi still. You know what? I'm still going to start off -4 to 4 on the x-axis and -5 to 5 on the y-axis. Looks good. So here we go. Here comes the graph. All right, I have a good graph there, but I'm going to get an even better graph by making a square viewing window. Folks, that's called a cardioid. Called a cardioid because it kind of looks like a heart. So what I'm going to do now is I'm going to go back to the chalkboard. While the directions in number 58 only ask, hey, what's the graph? We have the graph. But I have another question I want to ask about this graph. I basically want to know for what values of theta does the graph hit the pole. So let me head back to the chalkboard and finish this off. All right, number 58, just doing the graph of r equals 2 minus 2 sine theta. That was pretty straightforward, pretty quick. We used our calculator. We got this graph. I told you it was called a cardioid. Kind of looks like a heart. But I want to extend this one just a little bit. I want to do one thing here. Let's say I'm curious as to what values of theta would put me at the pole. Folks, remember in doing polar graphs to think that your r, your directed distance, is a function of theta. That is really, really important. So what values of theta have me at the pole? Well, think about it, folks. When you're at the pole, your distance away from the pole, r, is 0. So if I put 0 in here and say really what I'm saying here, by putting 0 in for r, I'm saying, what values of theta put me at the pole? And this is a friendly equation to solve. Add 2 sine theta to both sides, divide both sides by 2. And a theta value of pi over 2. That's what puts me at the pole. Kind of foreshadowing the next section when we look at the calculus of polar coordinates. But you're ready now to do the homework in section 12.2. It's calculus free, but it's really important to do these problems and understand what's happening with polar coordinates so we hit the next section, hit the ground running. So head off, do the exercises in section 12.2. Thanks for watching.